We are live. Please start.
Hello everyone, thanks for joining today. I am Manan and I'll be talking to you about how to do programming with a quantum computer. So I'll begin by sharing my screen. I'll start by giving you brief insights about programming with a quantum computer. So I'll start presenting now. I'll be joined by Naman, who is also a part of our team, and he will be giving you a live demo about programming with quantum computers. So let's begin. I'll just share my screen. Is it visible?
Yeah, man.
Perfect, perfect. So I'll just give you a brief intro about myself. And I'm an entrepreneur. It's been about a month since we have started this journey about Silicofella. So it's my company, and we are developing innovative solutions in quantum computing, be it healthcare, automotive, finance industry. So as we all know that quantum computing is going to revolutionize the world very soon, and I have started out this journey where I'll be bringing the academia, the research institutes, all of the government together as the president of One Quantum Bangalore. So it's been a very amazing journey for now, and I'll also share my experiences with you all so you can connect with me on LinkedIn if you want. And without further delay, I'll be starting out. So, firstly, I want to tell you all hello, many worlds. So, in quantum computing, it's not just hello world, it's hello, many worlds. Because quantum computing is totally different to classical computing, and they open up the possibilities to do computing in a totally different way as to what we are accustomed with classical computing. So, what makes a quantum computer so powerful? What are the unique properties of a quantum computer and what makes them so special? All of this we'll be discussing now. So, there are basically two concepts that we all need to understand first. One of them is quantum entanglement, and one of them is quantum superposition. So we all know that classical computers have been working on bits which are either 1 or 0 at one particular time. But quantum computers operates on qubits which are 1 and 0 at the same time, which means that we can do much larger computation given the fact that they exist in the superposition of 0 and 1. So just think about how is that possible? This is where the quantum magic comes in, where a state can exist in one in one the bit can exist at one point in two states. So that is the key difference. And the other one is obviously entanglement, which means that we can entangle one qubit with another, even if it is a very far position. So these are the two properties that we all need to know before venturing out into quantum computing. So this is how a quantum computer exactly looks, and it's very costly. It's about $41 million. So these machines are very expensive and they are very new. They are different to what high performance computing is, and especially given the fact that they are very rare in the market right now. So that is why they are cost very highly. And the IBM has a 127 qubit quantum computer, which they have launched recently. So it means that now we are entering into the era of quantum computing, which is called the NISQ era, which is noisy intermediate scale quantum computers, which are from 0 to about 100 or more qubits. So these are very noisy machines, and there is not a lot of advantage right now, but very soon we expect a lot of qubits to be inbuilt in these quantum computers, and we can do much larger calculations using them. So this is basically the stack of a computer. When someone runs an operation, it goes through a dilution refrigerator. So these computers are kept at very low temperatures. And then the whole chandelier, if you see on the right hand side, it goes to the quantum chip. So the only quantum element in a quantum computer is the quantum chip. And that quantum chip has qubits. So each qubit is basically an artificial atom. So right now we have reached the level of advancement in technology where we are capable of creating artificial atoms. And using these atoms, we can send microwave signals to them, and then we can create the quantum computer. And on the left hand side, you see the qubit. So that is the qubit that we are trying to manipulate using the microwaves. So this is exactly how the quantum chip looks. So if you see they are having the qubits. So I just wanted to give you a brief intro into quantum computing before we dive deeper into the quantum programming aspect. So this is exactly what a quantum chip looks like. As I said, it has readout resonators, it has the transmon qubit in it. So moving on, this is what Jake Gambetta has said about quantum computing, that in the last 60 years, what we have been doing for classical computing, we need to have that same progress in the next 2 or 3 years when it comes to quantum computing. See, when we had started out in classical computing, we had entered the age of digitization. And now we are going to enter the age of quantization, where industries that do not move towards quantum computers are going to be left behind because these computers are very fast, and even Google has demonstrated quantum supremacy in an experiment. They had said that quantum computers can do a task which classical computers will take 10,000 years and quantum computers will take just 10 seconds. So it was a random calculation that they did, but still that was enough to suffice that quantum computers can have a significant advantage when it comes to classical computing. So I'll give you a brief overview about the gates. So you can see these are the quantum gates, and using quantum gates, there is actually a mathematical algorithm, which means that we can do teleportation using a quantum algorithm. So quantum computing has the potential to teleport one qubit from one state to another, and this is the algorithm or the circuit diagram for that particular quantum teleportation. So if you see, there are three qubits that are there, and there is one register there are basically two registers and three quantum bits used over here, and a lot of gates. So most of you over here would might be new to quantum computing, so you won't be having that knowledge about quantum gates. So there are a lot of resources available online that you can check and get to know about a lot of these stuff. So we'll touch all of these topics briefly about what are quantum gates, what are matrices, and how we operate a quantum computer. So before that, I want to talk to you about exponential growth. So what is exponential growth exactly? Exponential growth is when we take one penny and we double the penny every single day. So I want you all to guess how much pennies will you have after 30 days? Just 30 days. So if you look below, you see that you have $21 million now. That is the power of exponential growth. So these machines grow exponentially due to the fact that addition of every single qubit in the machine means that the computational power increases exponentially. Whereas in classical computing, if you see, we need to double the number of transistors in a chip in order to exponentially increase the computational space. So that is the huge difference when it comes to quantum computing, the exponential advantage that we have. So whenever we are going to have, let's say, a 1,000 qubit quantum computer or a 300 qubit quantum computer. So that is going to have the computational spaces in those computer will be even if we combine all the atoms in the known universe, still we won't be able to come to that mark. So that is what some class of problems can be solved using classical computers, but there exists a totally different class of problems that will be solved using a quantum computer. So these problems can be simulation of molecules or be it simulation of drugs. So we can also discover new drugs. So there are applications in healthcare industry, there are applications in finance industries, as I said earlier, and basically every single industry that exists right now needs to go through the era of quantization. And how is that going to happen? It is going to happen with quantum programmers who are going to program quantum software. So the sooner everyone starts to learn quantum programming, the better it is for the whole quantum ecosystem to progress. So right now there is just about 127 qubits, as I said, and if we have, so suppose earlier we had a 80 qubit quantum computer, so that means even if we combine all the computers on Earth together, they will have still the less exponential space or complexity as compared to a quantum computer. So why should you begin your journey in quantum computing and start learning how to program a quantum computer? So the world's giants are already in the game. If you look at Microsoft are already on path to developing a topological quantum computer. Then IBM has significantly progressed in the field and they have come out with their own quantum computer. Google is heavily investing into quantum computing where they have come up with their own libraries and their own quantum computers. So the giants are already in the game and they are going to be recruiting people like quantum programmers very soon. So that is why you should start early into this field because there's also another thing that I'm going to discuss about, which is the first mover's advantage. So suppose I'll give you an example. If you're a car manufacturer and you have a access to a quantum computer, so you will be able to develop something unique, something that people with classical computers cannot basically do because they are limited to the classical resources. So if if you are a car manufacturer and you develop a body or a material for that car which is lighter than the materials that are there existing right now, then your car is going to be much faster than the other cars. And then due to the exponential advantage, you are going to become better and better with each iteration. So that is where if you rely solely on classical computers, you won't be able to catch up. And people are investing into quantum computing so that they can develop these IPs and have an advantage or an edge over other companies that are solely relying on classical computers. So that is very real, the first mover's advantage, and it comes to programmers also. The programmers that are going to learn this very soon are going to get a huge amount of benefit because they are accustomed to quantum computing rather than the people who rely on classical computing. So just think about what is capable with a quantum computer. We can actually use Shor's algorithm. So the algorithms that exist for classical computers are no longer applicable on quantum computers. To use a quantum computer, we need different algorithms. Even the search algorithm that we were using earlier is totally different when it comes to a quantum computer. See, I'll give you an example. Let us take four cards, out of which three are king and one is ace. So if we use a normal searching algorithm, we'll have n tries at maximum to figure out which one is ace in a deck of four cards, right? But if we use a quantum computer, we'll have it reduced down to just two tries. So that is all we need. So if we have a classical computer, we'll have to basically go through one card at a time, and at maximum we'll have four tries, and at minimum we'll have one try. So on an average, we need two tries, right? I hope you're getting what I'm saying. On a classical computer, we need two tries, but when it comes to a quantum computer, we can find out which card is ace in just one try. That is where the quantum magic comes in. And basically, if we are going to use these algorithms, like Shor's algorithm can basically break encryption, be it encryption of our normal banking software, our websites, or even some part of Bitcoin. So that is the power of quantum computers. And it is a threat to national security. But right now, we are in the progress of developing post-quantum cryptography algorithms that are going to help industries shift towards quantum computing algorithms, so that when we have a large quantum computer, we are resistant to that quantum attack or quantum threat. Countries are basically having an ideology which says, if you are a hacker, so obviously this technology can come in the hands of wrong people as well. So what they have is steal now, encrypt later. So if you have data, they will steal your data now and encrypt it later using a quantum, or decrypt it later using a quantum computer. So that is why it is a threat to national security, and India is currently a sleeping giant, in my opinion, and we need to work hard to become a giant in this technology. So there are companies that are working on this, and I believe that we all need to come together when it comes to this technology, and do something useful so that we can protect our nation. And apart from the dark side, we also have a good side, which is it can be the foundation of future economy. So India plans to become a 4 trillion economy very soon. And with the help of quantum computing, we can actually achieve that goal. So it comes down to how fast we can actually accelerate the discovery and all the aspects into quantum computing, and become so that it can be the foundation of our future economy, so that all the computing will rely solely on quantum computing. So that is a far-fetched goal, to be honest. Quantum computing is a 10-year-old game, and we are just getting started right now. So the opportunities are there. There are wide range of opportunities if you start looking. So it's a foundation of future economy. As I said, I'm going to iterate this point one more time because it is very important for the future of our country. And the climate change, if you look at how fast the climate change is happening in the world right now, so we can use quantum computing for a better future as for the whole world as a whole. So I'm just going to go through what different types of advantages are there in quantum computing. So we can actually, there are fast quantum algorithms, and we have to hit the target in the middle, which is where we don't have any fast classical algorithm, but we do have a fast quantum algorithm, and we have to find a useful problem. So if we hit the sweet spot in the middle, we'll be able to find some advantage, and the advantage lies basically on the how we can improve the prefactor of the polynomial, or we can exponentially reduce the polynomial. So if you have a look on the bottom, there's the example over there. You can have a look, and you can see that quantum computing. So if you look at Stone's algorithm, it basically is exponentially faster in terms of encryption. So that is where it is real. The advantage is real, but we are yet to have the quantum computer that is capable of doing that. So coming to the programming part now, so I'll shift now to the quantum programming part. We still have a lot of time, so we just go through all the quantum gates that are there. In classical computing, we had the X gate, the Y gate, but over here in classical computing, I'm sorry, we had the NOT gate, NOR gate, AND gate, but in quantum computing, we have X gates, Y gates, Z gates, and like that. So these gates are basically matrices, and we can do multiplication on these matrices. So that suppose if we are given one gate, and then after that gate we are given another gate. So it's basically just matrix multiplication where we multiply the gates and get the result. So it's very easy. You have to have the understanding of linear algebra and and linear algebra and matrices. So these two things you need to have a strong background in, and I think that we are taught these extensively in our courses in colleges and schools. So I believe that all of you over here have this particular set of knowledge. So you can start you have the prerequisites. You can start diving deeper into the world of quantum with the help of the knowledge that you already have. So as I said earlier, the X gates, Y gate, Z gate, and the H gate is very important because it helps us in putting the state into a superposition state. And the C naught gate is very similar to what we have been doing in classical computing. So it's just that we need a different mentality, a different ideology into start when we are start working in quantum computing. And it can be very difficult, especially if you're starting to do this all alone. In terms of it can take you a lot of time to learn the basic concepts. And there are not many institutions that extensively teach how to program. I can name a few that are doing it, but in terms of the country, we need to step up. We need to have courses implemented so that we can start learning how to program a quantum computer. And you have the prerequisites. You can dive deeper into the gates. As I said, it is very a different mindset that we require while starting into quantum computing. So I'll give you the basic languages that are there. There's Qiskit, then there's Circ by Google. So Circ is also a programming framework that is being used right now. Then we have D-Wave annealers that are doing it. Apart from D-Wave, we also have Rigetti. They have their own programming language. And then there's Pennyling, another programming language that is being developed by Xanadu. So just like that, there are different, whole different kind of programming languages that you can use to operate a quantum computer. So it depends on you which one do you prefer. So the most the programming language that is known to all, especially in quantum computing, it's Qiskit. So Qiskit is Quantum Information and Science Development Kit, and using that also we can operate quantum computers. So we'll be having a demo, as I said earlier. So we'll be having that demo on Qiskit only. But right now, I'm going to take you through to how you can do programming with CERT. I've told you about quantum gates. I've told you that they are basically the set of matrices that are there, and then we basically need to come up with a circuit that helps us build our quantum program. So building that circuit requires the knowledge of qubits, and so this is exactly what first it's basically a program to help you understand how we can use quantum computers to differentiate the classical algorithms and quantum algorithms. So over here, what we are doing is we are putting out random points on a graph and then finding a route in that graph. So it's a traveling salesman kind of a problem where we have a traveling salesman who is traveling from point A to point B, and then he has to return, complete the Hamiltonian cycle, and we have to do that in the shortest amount of time. So there are heuristic algorithms that are there right now, but in terms of an algorithm that can specifically give the right answer, it doesn't exist because the exponential increase is there in the computational need to solve this algorithm. So suppose if we have 10 nodes, it is easy to solve. But now if we have 1,000 nodes, think about the possibilities. Think about the combinations that the salesman needs to go. So if there's one city he needs to go, it is going to take and come back to the same city, traveling through thousands of cities. So which city should we go first, and then which city should we go next? So there's a whole different combination that exists that the salesman can take, but they cannot be used to solve. They cannot be used as a problem to solve on classical computers. We need quantum computers for these set of problems. And this is one example, a small example of how we can use that. I hope you all can see me. I think there was
Yeah,
some
Manan.
kind of a. All right, perfect. Yeah. So coming back, we were talking about our problem, how the traveling salesman problem. So now if we use a quantum, so I'm going to show you now the quantum algorithm. So we import circ and then we define the circuit and then we solve the problem. We are solving it on a simulator. So Google has this thing called a simulator, and every programming language will have a simulator. It is essentially we are mimicking the quantum hardware on our classical machine. See, right now we are existing in that time where we can basically emulate the quantum environment on our own classical computers. But as I said, as I showed in the presentation, that we can only simulate up to 30 qubits, because after that our computers are no longer sufficient enough. Even if we combine all the computers together, still we won't be able to do that if we had 80 qubit quantum computer, as I said earlier. So we can just, to start learning, to start our journey into quantum, we can use the simulators or the emulators, so that we don't have to spend a large amount of money using quantum computers. So Qiskit is basically very expensive. Qiskit runtime, it's $1.4 per second. So it comes down to about 4 lakhs an hour. So you can't just to experiment with quantum computing or to get started with quantum computing, you won't be able to spend that much amount of money, right? So that is where we use simulators to simulate the whole algorithm to get the result. Especially, and these results are accurate because they are noiseless. So we get a pretty good result out of it. So this is another platform apart from Google, which is the classic platform. With this platform, we don't have to dive deeper into the gates and all. So if you want to get started without learning the gates, if you have quantum programming language, you can just dive deeper into it, because manipulating each and every qubit single at creating those circuits on a large scale for 1,000 qubits is no longer feasible if you do it on other platforms. So that is where Classic is also an industry known framework which you can use from AWS and start programming into quantum computers. So this is the code for implementing basically a VQA problem. I'll not dive deeper into the algorithms, but I do touch upon the basic algorithms that are being used in the industry right now, so that you can have a basic knowledge of exactly what are the quantum algorithms. So this program is just to show you all exactly how the classic platform works. So this talk is essentially to let you understand what different type of programming frameworks are there and what is being done by other companies out there. So so combinatorial optimization problems are the type of problems that we can solve. So I spoke about the traveling salesman problem. It's a combinatorial optimization problem. And there's also another problem of sensor positioning in the cars. So we have autonomous cars and we have to position the sensor on the car in a way, right? So that we get the optimal autonomous car. So where do we put that sensor in the car? Which position do we put that sensor, and which orientation should the sensor be in? So if you look at it, there exists infinite, not infinite, but there exists a lot of possibilities where we can place the sensor, and that is where the combinatorial optimization comes in to help us basically solve such kind of problems on a quantum computer. So these are the problems that are just to give you a few examples. And the algorithm, as I said earlier, there is an algorithm that is called QAOA, which is quantum approximate optimization algorithm, which we can use to solve these kind of combinatorial optimization problems. So it has like a mixer Hamiltonian and a cost Hamiltonian involved, and we have to just keep on iterating and get the optimal answer. So this is an algorithm that you can start learning on once you learn the basics of quantum programming. So these algorithms are extensively used in the industry to get to know to solve problems. So I'm just touching base upon over here so that you can have a brief understanding, as I said. So yes, coming to the essential part, why should you learn how to program a quantum computer? As I said, it's the technology that is going to be creating the future for the whole world. So that is where if you start learning now, you can help build a better world. You can help solve some of the most challenging problems that exist in the world right now. And that is why you should get started. If you have that passion, if you are passionate about technology, if you think that you can change the world, you should start getting into quantum computing. You should start learning these technologies so that you can have that impact onto the world. So there's a talent shortage also going on in the quantum industry, where the demand for quantum programmers is three times the the supply of quantum programmers. because there's not many people who, especially if you talk to industry people, when we first talk to them, they are like, oh, okay, what is a computer? So we have to explain them about the technology, the new technology is coming, it's a quantum, it's faster than the classical computers. So that is why people are not aware of this technology, most of the people. But some people are, and that is where if we start learning, we can help that particular solve the problem of the talent shortage that is existing in the industry right now, and help the industries that are there. So we also as a company, when we try to hire people, so we see if they are good at programming with quantum computers, if they are certified developers by IBM, and only then we hire them. So we need to, and when we see the applications that are coming in, so there's not many people who have the right skills. So that is where we can learn this technology and have that first mover advantage, as I said earlier. So it is essential for all of you to, if you have that passion, as I said, to dive deeper into quantum computing. And there's a lot of opportunities for growth. It's very new, so not many people know, as I said. So you can have that career progression early on, where you can progress your career at a very fast rate. So this is where the opportunities are there. If you look around, you find a lot of jobs for quantum programmers, quantum developers, quantum researchers. So it's just that you need to have that right skill set with you. And obviously, it's a very high paying job. Quantum computers themselves are worth, as I said, $40 million. So the average cost is about $75,000 per annum. And in India, there's not a lot of the development is very less when it comes to big game companies that are doing it in India. So I'm quoting this about the international job. So that is the average, $75,000. So it's very high paying, and that's the early software, early stage quantum developer. So that is what it is, a very high paying job. If you learn these skills early on, you can earn a lot of money for yourself, for your family, and that is where the money part comes in. So now I'll be handing over to Naman. So Naman is a software developer at our company who has joined recently. He's very passionate about quantum computing, and he has in his spare time he does quantum programming, and not just in his spare time. It's what he loves to do. He breathes quantum. He loves quantum. So that is why Naman is here today to show you all a quick demo of quantum computing. So Naman, are you here with us?
Yeah, I'm
All
here.
right. So I will stop sharing my screen for now, so you can start sharing. And why don't you give them a demo of quantum computing? The stage is all yours.
Yeah, sure. And thank you for the wonderful introduction, Manan. I'll just quickly share my screen and start it. So I
So
hope my screen is visible now.
quantum tunneling.
Yeah, okay, great. So today we'd like to make a demo on quantum tunneling. Now, this is not the kind of thing you would see uh, if you're just starting into quantum, because you would hear about Shor's algorithm, you would hear about Grover search, quadratic speed up, exponential speed up. But this excites me, and I'll tell you why. Because this is kind of a like the realization of a dream coming true, and that dream was by Professor Richard Feynman. Now, he proposed that we somehow harness quantum physics to build a powerful kind of computer that could simulate the quantum systems. Now, that was around 50 years back, and today we are here, sitting in front of our laptops at home doing this sort of thing. And this is really remarkable how the technology progresses and the kind of wonders we are capable of. So let's just quickly dive into this and see the results by sitting at our homes. So quantum tunneling is a phenomenon in which a wave function can propagate through the potential barrier, which is not possible classically. And that's what we'll do today. So this demonstration is based on the works of Narendra and others, and you can look up this. It's a wonderful paper. I enjoyed reading it. I'm sure you guys will do as well. And so today we'll be using a very simple algorithm, I would say, to do this. But there are, as Manan mentioned in his presentation, we have variational quantum icon solvers, variational algorithms, QA/OA, to do much more complicated, complex kind of things like estimating the ground state energy of molecules, predicting structures of drug molecules, and all that. So we'll be doing a simple demo today just to give you an idea of how it happens and what it actually looks like programming a quantum computer. So first I'll just quickly go over the theoretical protocol that is being implemented here, and then we'll see the code example of that. So what we'll be doing today is simulate this kind of environment where we have a single step potential, and we need to demonstrate that quantum tunneling is possible through this barrier. Now, all the information, all the knowledge that we'll need for this is encoded in in this equation right here, the Schrodinger equation, the holy grail of quantum mechanics, I would say. And as we all know, this is a Schrodinger's equation for a single particle, the time-dependent equation moving in one-dimensional space. So what we see, this notation here is called the bracket notation or the Dirac notation, and psi is the wave function, which is time dependent, and h hat is actually the Hermitian operator, which gives us the evolution of that wave function. So writing this out in a much more expanded form, we can see that after a time delta t, the wave function evolves according to this equation, and it is given by exponential of the Hamiltonian times the initial state function. So the h hat operator is actually composed of the kinetic and potential operators in a single particle system. And so we just write it down like that. And now what we need to do is to discretize this continuous space in order for us to be able to do it on a quantum computer, because at the end of the day, the quantum computer only gives us results in the form of zeros and ones, which are discrete binary elements. And so to do that, the authors propose this kind of discretization strategy where we discretize the wave function between the binary states. So a binary representation of a wave function in a 3-qubit system would look somewhat like this. Now you could think of this as the kind of state space in which the quantum particle is allowed to move through, and what we'll be doing is we are going to put the particle in one of the states and then put some barriers in other states and see that if that particle can move through that state or not. And to do this, we will need to implement the potential and kinetic energy operators. Now, in terms of the equation, they look really simple, but what we need to be able to do is put that in the form of the gates, which is the gate model of quantum computing that we are going to be presenting today. And to implement the potential energy operator, we approximate that operator as a magnitude of that operator, which is the small v that you see here, times the poly z operator. Now you could find the details of this approximation and the equation in the paper. I will skip that for the sake of time. So similarly, we approximate the kinetic energy operator in terms of the momentum, and we discretize the momentum later on, and finally we will arrive at an equation something like this, which enables us to be able to build this model in the form of quantum circuits. So the different elements in this equation are QFT, which is the quantum Fourier transform. Now, this is nothing but a simple basis change. So, as I mentioned earlier, what we can only extract information in the form of binary bits, zeros and ones from the quantum computer. But in the process of solving a problem, we need to change the basis from the 0 and 1 states And that is where QFT comes in handy. And QFT is used in a lot of algorithms, including Shor's algorithm. It's wonderful. If you're interested, please check it out. So we apply the QFT and then we apply the kinetic energy operator, and then we change the basis back to the computational basis, and then we apply the potential energy operator. So the details of all this are beautifully explained in the paper, and I would really suggest you guys to take a look at it. And finally, what we arrive at is the simple equation of this sort, which says that the time evolution of a wave function is can be implemented using this sort of circuit. So now we'll just quickly go through the example of go through a solid example to see if it works. And so we first what we are using is a Strangeworks platform, and it has great UI, and it's not scary for beginners, I would say. So go ahead and try that. It's really wonderful. So initially we just import all the things that we require, Qiskit, quantum circuits, and some visualizations and some execution helper functions, I would say. And later we define the block of code which will allow us to implement the QFT and the inverse QFT functions which were required. So all these implementations are standard, there's nothing new about it. And now we just take a concrete problem in which we assume that the mass of the particle is 0.5 units and the magnitude of the potential barrier is 50 units. And what we do here is to simulate that in a to evolve that circuit with time, we basically implement it in terms of multiple steps, and each step sort of runs for like 0.1 time units. And now let's build the quantum circuit. So to build a quantum circuit, there are three essential parts, I would say. The first part is the state preparation, the second part is time evolution, and the third part is measurement. So state preparation, what it basically means is that you start clean. You wipe off your slate and you begin everything at a simple state which you can easily manipulate and work with. So you start with the 000 state, which is pretty simple. You apply reset operations, you clear your quantum registers and get this state. And then what we'll essentially be doing now is that we put that particle in the state 0, 1. The reasons for this, I'll just explain it in a moment. So we move the particle from the 0, 0 state to 0, 1 state. And now what we need to do is time evolution. And to do that, we apply a series of potential and kinetic energy operators, as simple as that. So to apply the potential energy operator, we use the RZ gate, which means a rotation about the z-axis of the Bloch sphere. And this basically puts a potential barrier for the states 0, 0 and 1, 0. So you can imagine this to be a particle at 0, 1 state, and on its left and right side, if I may, you can imagine that there are potential barriers of magnitude 50 on the states 0, 0 and 1, 0. And then we just do a bunch of operations using quantum Fourier transforms and inverses, and then apply this kinetic energy operator to. And finally, what we do is perform measurement. So this entire potential and kinetic energy operators are applied for 4 times for each of, let's say, 0.1 time units. Now all these values that you see here, pi square by 8, pi square by 4 and all that, they are results of us specifying a concrete problem instance and some basic calculations, and I would again suggest you go back to that paper and dig in for yourself because it's really wonderful. And finally, we perform the measurement to be able to get that result in the form of good old binary strings. And now to simulate this circuit, we are demonstrating it on the Quantum Simulator, which is basically a classical simulator capable of uh, mimicking a quantum computer. And we are doing it for 1024 times. And let's just see, we have everything ready. Let's just see, I hope I get the right result. Okay, it's running, still running. All right, okay, we have the circuit right here, and there you have it. What this essentially means is that this is a probability distribution of the different states that measurement gave us. So out of the 1024 times that we performed this experiment, 46 times we resulted in the 0 0 state, because quantum is probabilistic, and the 0 1 state resulted in 267 times, 1 0 state resulted only 9 times, and the 1 1 state resulted 702 times. So what we see here is basically we started in the 0 1 state, and somehow we got to the 1 1 state in spite of us having a potential barrier at 1 0 state. Isn't that amazing? How you could see for yourself that the quantum tunneling phenomenon just by sitting at your home in front of your laptops. So that's all for the demo. Uh, I hope you got at least a little interested in quantum. Thank you. Okay, so now we'll just quickly head to our website and
Yeah. I think there's a question in the audience that is asking us, Naman, that how they
yeah,
can start quantum journey and how they can learn quantum computing. So firstly, just take them through the applications of quantum computers. So just click on application and so that we can see what are the different applications. And then if you guys are interested in learning about quantum computers, then we are helping you to become a certified developer by IBM. So just scroll down and basically help them for themselves.
yeah, you can see applications of quantum computing in all the technologies, Web3, blockchains, solving optimization problems, simulations.
So if you
You can
are
go ahead and visit.
so just click on learn so that they can learn quantum computing. So I hope you guys have got a glimpse of what programming with a quantum computer actually is. So if you are interested, then we do help you become a certified developer by IBM. We'll help you become the master of the quantum verse. So you guys can register for the course. The registration is starting out very soon. So just make sure that you guys register and get to know about how to program a quantum computer. So do check out our website. You'll get all the details over there. If you guys are interested, you can also reach out to us via email at communications@silverfeather.com, and then you can also message me on LinkedIn, so I'll be available. With that, we'll be closing our presentation, so you can stop sharing, Naman. And if you guys have any questions regarding, you can ask me now, so I'll be happy to answer. Let's see if we have any questions. Are there any questions? Yes, someone is messaging. I think on the YouTube channel, I'm not able to see it. Can anyone let me, if they have any questions on YouTube? So I'll just quickly open the YouTube link.
Yeah.
So I think Paras is saying that quantum computing is still in early stages. Basically, there's no use to make a career. I think that it is in early stages. That's correct, but you can make a career out of it. If you see, there are thousands of jobs available right now, so you can also apply if you have the right skill set. So then we have how the quant from Sudarshan, we have how the quantum computing course can be adopted from India. So just check out the website Sudarshan, you'll get all the details. There are also a lot of resources available for free. You can check out on YouTube if you are interested. But we are obviously giving out live lessons to everyone so they can learn from mentors and Qiskit advocates that are out there. So if you want to learn quantum computing, we are here to teach you. We are here to address the shortage, and then we will make sure that you get hired in our company. So that is where it's a long, long journey. As I said, and if you start early, it is going to benefit. Can NCA lead to quantum computing and acquisition of quantum physics and quantum programming learning in NPTEL? So that is something we have to ask from the NPTEL team. The team is here. If they are willing to answer, they can answer. But still, they have their own quantum computing courses. You can check them out. It's very amazing. The learner explain everything in detail. So you can check that out. What level of coding should we have to learn quantum computing? See, as I said, you should have the knowledge of matrices and linear algebra. Apart from the coding side, you need to know Python. So that's all. Once you know Python and the basic prerequisites, then you can start diving deeper into Qiskit and all the programming languages that are out there. So the whole journey, if you start alone, it take you about 6 months or 1 year as well. So you can start alone or you can learn with your peers. You can learn in a fun and interactive environment. So being a 12th grade student, how can a person learn quantum computing? See, I think you are at the perfect stage right now to get going in quantum computing. Just find some courses you can study. Just go to the IBM summer school. That is something you can attend. And basically, the people that are in their early stages of their career, they can make a good career out of themselves for themselves in quantum computing. So you are at a very early stage, and I feel very happy to know that you are interested at a very young age. Are there placements after MTech in quantum computation? What is the average salary? So yes, there are courses in India that are there. You can check them out online. This IISc is doing it. IITs are also now coming into it. So you can check them out. You can do that course, and then you can apply for jobs at IBM, Google, or startups around the world. So the opportunities are endless. You just have to have the right skill set, as I mentioned earlier. How to start quantum computing. To start quantum computing, we are here to help you out. This is the start for you, for me especially. Now you are here, so your journey essentially started out with quantum computing. And if you need any help, do reach us out. Do reach out to us. I'm doing BS from IIT Madras. How can I learn this? Will you be collaborating with IIT Madras? So right now we are not collaborating with any research institute, but we are open to collaboration. We have started this out early. We are also in the early stages. So we are open to collaborations. It's a long journey. If we have the right connections early on, it is going to help develop the ecosystem in a better way. How can we learn the complex mathematics that Naman showed? To learn the complex mathematics that Naman has showed over here, you need to first learn the basics. So once you learn the basics, then you can dive deeper into the algorithms. Do check out the Qiskit textbook. IBM has a textbook, so you can check that out. It is very interesting for people who are starting early. Then there are a lot of books that you can read. So there's one by Jack Hillary. He's the CEO of Google Sandbox AI. So Google has their own spin-off from a company that's called Sandbox. So their CEO has a very interesting book on how you can learn quantum programming by Jack Hillary. So just write that down. Which language is used in quantum programming and how is it different from the traditional language? So as I said, Qiskit is the language that Naman has showed its quantum information and science development kit. So it is basically we are using Python only. It's an extension of Python, not an extension, but we are using Python basically to develop quantum computation. So all you need to know is Python. That's all. What is the duration of the course? So right now, the duration of the course is 3 months. So we fast track your journey into quantum. So if you want to learn, you can learn in just 3 months. You can become certified by IBM. So IBM has this certification that you can do. So you just have to, learn first. So we'll help you learn. We'll make sure you understand all the basic concepts. We'll have assignments, MCQs, mock tests. So our team is there to help you basically learn and grasp the important concepts. So when you take the IBM certification exam, at that time you can pass the exam with flying colors. What is the price of the course? So right now the course is very is about, you can check the website, you get all the details regarding there. So there are different people that are different organizations that are pricing it at 1 lakh in terms of India, but we have kept it very cheap because we promote education. We want everyone to learn quantum computing. So it's just about 25,000 for now. And if you want to learn, you can start with that. So, with especially with the new batches coming in, we'll be increasing the price as well because we know that right now 25,000 is very cheap because quantum computing is essentially the future and we are teaching you the skills of the future. So if you start now, you will get it at a very, very good price. What is the duration? What is the price? What language? So I think I've answered all your questions for now. There's not, when is the batch going to start? Like after registration immediately. No, the batch is going to start from first, so first of September. So we are so if you can register now and then you can get there. In which areas we are most close to have real use quantum computing. So in terms of simulating molecules in chemistry, the nearest applications are observed because we are using quantum computers to extract properties from the data using quantum data. So we can see more about the molecules, we can simulate them, we can essentially develop new drugs as I told earlier. So chemistry is the nearest application in my opinion. All right, guys, we are nearing the 1 hour mark. I think I can.
I'd like to take one question, Manan. I think you missed that.
All right.
It was some time back, and it asked like it is a very interesting question. It says, "Do you see QC replacing classical computing?" And this is really interesting because uh, quantum computing will never replace classical computing. You
Yeah,
will
that's true.
never, right? You will never be working on a quantum computer at your home, but you can work from your home on a quantum computer. And this, the reason for this is because what we do with our laptops today, for example, this meeting, the presentation, all this is really simple and efficient in the way we are doing it right now. And there's no point in complicating it with a quantum computer, and it could become insanely hard unnecessarily. So, what will happen with quantum computers is that they will become much more suited to particular class of problems like complex optimization problems or quantum physics simulation problems, something like that. And they will work hand in hand with classical computers to give the best results. And that is another new area that's coming up, hybrid classical quantum computing. So, yeah, that's all I had to say about that.
Perfect, perfect. I think that was a very nice intro into hybrid because the future is hybrid for now. So thank you everyone who had joined today. And I also want to thank IIT Madras BSc degree program for giving us the opportunity to present today. So it was a wonderful session. I enjoyed answering all your questions. If you have more questions, do reach us out at any time. All right. So I think we'll take off then. Aishwarya, are you there? All right, Naman, let's take off for now. I think we've reached the hour mark, so the link will be getting closed. Thank you all once again. See you soon. Bye bye.
Bye bye.